Good morning. So I want to actually skip one section. I will come back to it later if we have time, but I want you to learn about these techniques of integration techniques. There's no I here. Yes, so techniques of integration is actually an important lesson. And mainly these things that you see in Math 5 book are not part of this course, I think. So you will see them in the university, but it doesn't hurt if you start learning about them right now. These are in the book, but I might go a little bit beyond or in a little bit different order. So what is the meaning of techniques of integration? So in Swedish system, we talk about primitive functions rather than two types of integrals, yes? In a Swedish system, you call this an integral. Yes. And then if I ask you to calculate this integral, one main tool in our hand is to use the Newton's formula to find a primitive function for this, which we denote by capital F. All of them, of course, are standard notations. And then you write from A to B, and then this becomes f of b minus f of a. So in principle, if you want to calculate an integral, we need to know a primitive function for that integrand to be able to continue the calculation, yes? So, in principle, in Swedish system, they call this integral, but to be more precise, that is called a definite integral. So, this distinction is not necessary in the Swedish system because you don't talk about indefinite integrals. Okay, so this is the adjective that I use for this from now on. And instead of talking about a primitive function, we denote it by this symbol. Okay, that's also an integral. So when I write f of integral of f of x, just d of x, this means that I am looking for all primitive functions for f. So this means that the set, or I don't know how to call it, the collection of all primitive functions of f, of little f, yes? And here, the role of this dx is just to make clear which variable you are working with. Might be in a definition of f of x, you have more than one letter. So this tells you that, okay, no, the variable is x, not the other. Okay. So instead of talking about a primitive function, or I can call it antiderivative. Some people call it antiderivative. This is a good name. Why? Because it gives you, it's against differentiation. Yeah. So you get a function that whose derivative is f of x. So some people call it antiderivatives, or I would say that it's an indefinite integral. So let us stick to this convention that we can call both of them integrals, but one of them with limits is called a definite integral. The other one without limits is called an indefinite integral. An indefinite integral is what we have called so far a primitive function. So it's nothing, yes, just a simple notation. So this means that if I ask you to calculate this integral, what I am asking you to find all primitive functions for this function. That's it. And you already know what are all primitive functions for x squared. So you know that a primitive function for x squared is x to the 3 divided by 3, because you are looking for all of them, you add a constant c at the end. So for the time being, that's just a mere change of notation or terminology, yes? So when we talk about techniques of integration, it means that we are looking to develop our tools to be able to calculate more, the primitive functions are more type of functions, yes? And of course there are a lot of these tricks and techniques. You will learn them more precisely when you go to the university, but there are some important things which is mentioned in the book, and they're really, really important to know. So I want to go through them. But I will reorganize them a little bit, because they have started with a very important trick which is called integration by parts, and then they have presented a technique called method integration by substitution. But I prefer to start with that one and then come back to partial integration by parts. Okay, so we will learn this one. So the first method that I want to discuss today is this. And probably we will not have time to go through the other method. We will cover that hopefully on Thursday. Okay, so here, method of substitution. By the way, I didn't so I think that these are very simple for you. For example, if I ask you to calculate an integral of 2x squared minus cosine 2x dx, I don't think you face any problems. What do I mean? I mean, give me a primitive function for that function. That's it. And then you know that for finding a primitive function of that one, you can think individually, this one and that one separately. So what is the primitive function for the first one? It is just 2x to the power of 3 divided by 3. And what is a primitive function for that? So you write minus 1 over 2 sine 2x, and that's plus c. So this is, I'm not doing anything new. I have just changed the name of primitive function to this indefinite integral, yes? Okay, so now what is the method of substitution? So that the method of substitution is actually the chain rule version of integration. Okay, so if I ask you, so do you remember we had this formula which we called the chain rule? So we had f of g of x totally prime is equal to, you can move the prime here, f prime of g of x, but you have to pay the price to multiply by the derivative of what we call the inner function, yes? So this tells you that if you first replace x with gx, it becomes a new function. If you want to differentiate the new function, what you need to do is to first take the derivative of function f and replace x with g of x, and then multiply by the derivative of g of x. That was the chain rule, yes? So what does this mean? It means that if I ask you, can you give me a primitive function of f g of x prime, a primitive function of this is the function itself, yes? It's clear. When I ask you, give me a primitive function of this, I am asking you for giving me a function whose derivative is this. So it is very clear by definition that is your function, yes? If I take the derivative of this function, this becomes. So in this new language, what I can write, I can say that the integral of this combination is equal to that. But of course, I have to add a constant at the end. Yes? But now, instead of this one, I can use the chain rule, okay? And this gives me this formula, which is the substitution formula. Okay, so this becomes the integral. If I want to expand this, this becomes f prime of g of x and g prime of x d of x is equal to f of g of x plus c. That is the formula. It's not something we discovered now. We have just written it in a different notation. But that's the chain rule, and that's the immediate consequence of the chain rule. So you have a derivative here. So as soon as you see this very particular combination as your integrand, The answer is ready-made, yes. The answer is f of g of x plus c. But this doesn't be always so, it is not so every time always easy so to detect this pattern. So today's lesson is to give you some examples so that you can train your eyes to be able to catch that pattern so that you can use this formula properly. Yes? Okay, so this is the formula we want to practice today. Okay, so let us start with a very simple example. So for example, I ask you to calculate the integral of this function. Okay, if I have given you power of 2 rather than power 100, I would call it even a Mat 3C problem, because if I give you power 2, first you spend a little bit of time to raise it to power 2, and then you multiply this 2x inside the expansion, it becomes a polynomial, and you calculate the primitive function term by term. So that's extremely simple. But now it's completely clear that this method, even though in principle is the same, but it is really, really tedious or sometimes impossible, yes? So if I want to raise it to power 100, I am facing to 2 to the power of 101 terms if I want to do it naively. If I want to use the Newton's binomial theorem, there will be 101 terms involved, so that's also huge. But the point is that to train your eyes to be able to detect that pattern, okay, quickly. So first of all, what I am asking you to give me all functions whose derivative is equal to that one. Okay, so you see the pattern, yes? This expression that you see here, if I introduce a g of x to be x squared plus 1, if I introduce another other function to be f of x is x to power 100, yes? This means that this expression that you see here is what is, no, so that is not correct. That is a little bit tricky than that. So let me write a little bit a strange function. I want you to learn why this formula is useful, but I teach you a better method, okay? So that's why I'm myself confused, because I never do this, okay? Oh, sorry. X to power 101. Okay? And now let me ask you this question. What is f prime x? What is f prime g of x times g prime of x? Let us calculate this. Of course, I'm not saying that it is easy to think about these functions. I will teach you how to do it. But assume that I have given you these functions, and now I'm asking you to calculate this. I want to convince you when you calculate this, you will get this expression back. Okay, that's my point. So let us just do that. If I want to do this, I have to calculate g prime x first. So it's very easy. So g prime x is what? Is just simply 2x. And then for calculating f prime of g of x, what I'm supposed to do? I am supposed to take the derivative of function first, so I'm doing it. But this is easy because 101 goes down, that 101 will cancel that 101, and then this becomes x to the power of 100, yes? But this is f prime of x. I want to calculate f prime of g of x. Yes, so what is f prime of g of x? F prime of g of x, it means that go to your f prime and replace x with g of x. So it becomes g of x to power 100. But what is g of x? It is x squared plus 1 to the power of 100. So I hope that you agree with me that this is the case. If I ask you to calculate the question mark, you would say that instead of f prime of g of x, I write this expression, and instead of g prime, I write that expression. So you get this. And this is exactly what is appearing here. So is that clear? So it was not actually hard that much if you have a little bit of experience. So then it means that if I ask you what is the answer to this integral, it's on the board. What is that? It is f of g of x plus c. So the answer to this integral question mark becomes f of g of x plus any constant c. But let me just write what is f of g of x. F of g of x means to go to f and replace x with g of x. So the answer would be 1 over 101 x squared plus 1 to the power of 101 plus a constant c. And so that is all functions whose derivative is equal to that. Is that understandable? So, but I want you to see that if it was just x to the power of 100, it was nothing. You just immediately told me x to the power of 101 plus over 101. Okay? But if 2x is not here, you are not allowed to say x to the power of 2 plus 1 to the power of 101 divided by 101. The answer is this one only if you have this extra 2x there. Otherwise it is not working. Yes? But this seems very convoluted. No, but this method is much easier than that. But I just want you to understand, might be detecting that pattern needs practice. And I would say this is the most important trick in techniques of integration. Even though you start learning a lot of different more advanced techniques to calculate integrals, but believe me that this is the most important formula in all integration. Okay, if I want to solve this, I will never do it like this. Okay, what I do, I will start changing the variable. So the method of substitution, I substitute another variable here. So what I would say that, okay, let me take g of x to be u, a function. So I'm just replacing g of x with a new variable, substituting g of x with a new variable. So if I take this one to be u, then this will read f prime of u, and then this becomes u prime, and then this becomes d of x. On the right hand side it becomes f of u plus c. Yeah, so that's a simplified version of that formula. And that is common to write u prime dx to abbreviate it with just simply du. So in the book, so let me clean this is not prime. So this means that some books write it in this form. The integral of f prime u du is equal to f of u du. F of u plus a constant. By the way, that is not strange, because I am asking you, give me all functions whose derivative is equal to f prime. That is f. Yes, so that's nothing actually. So it means that, but you need to be able to detect this pattern. So let me solve this problem once more to let you understand what is going on. So let us start from here. I want to calculate this integral, the same method, but a little bit different. So I would say that I look for a function there so that its derivative somehow is also appeared in the expression. If you think in that way, it's not that hard. Yes, it is clear that if I take this in u in my head, it's a good choice, because the derivative of u is 2x, which also appears somehow in the integrand. Yeah, so what I do, I would say that let xu be equal to x squared plus 1. This is the first thing that I introduced in solving that. And I told you the trick. You look for a function whose derivative is somewhere appearing there, and then this becomes x squared plus 1. And then what you need to do, you need to rewrite your integral only in terms of your new variable u. So you substitute everything with u. How? The rest of it is algorithmic. It's simple. What you do, you take the derivative of that with respect to x. So, okay, and I want to skip this part. Let me just do it properly first. So I take the u prime, it becomes 2x. Yes? And I multiply it by dx. And I told you there is a better name for u prime dx, we call it du. Yes? And then it becomes 2x dx. I don't want you to spend time on it. So the way that you think, you would say that I take the derivative of this one with respect to u itself, which is 1. This is the trick. Make it faster. It is 1, but you multiply it by du. And on the right-hand side, you differentiate this one, 2x, but you multiply it by dx. So that you see 1 du, I can write du, and I get the last line immediately. So you can save some time. But this is the proper way of doing it. Okay, so I would say that this, then du becomes 2x dx. And then the question mark is the integral of 2x, x squared plus 1 to power 100 dx. The only thing that you can do it in your head is to rearrange them, because that's a product, so it doesn't matter how I write it. I would write x squared plus 1 to the power of 100, and I put 2x next to it, even though, so you really don't need to write these things, but I'm just doing it once so that you understand what's going on. So I just rearrange them, and instead of this expression, I can write integral of u to the power of 100, but instead of 2x dx, I can write du. So now this integral, I can use the rules that we have learned so far. Why? Because I am interested in primitive functions for u to power 100, but this time u is considered the variable. So it's exactly like that u is playing the role of x. So what happens, I can write 1 over 101, and then I can write u to power 101 plus c. But you shouldn't forget, because everything was in terms of x, after you did this, you have to switch back to the original variable, which is x. So it means that at the end, you have to replace u with x squared plus 1. So it becomes 1 over 100 x squared plus 1 to the power of 101, and then plus c. Yes. So I want to give you some examples to practice this. I would say this is the most important, but sometimes it is not that easy to detect the pattern. Yes? Any questions here? So what is the whole thing? Is that try to find a new variable so that when you do that change of variable or substitution, you end up with an integral so that you can immediately calculate its primitive function with regard to the new variable. And whenever you did it, you just replace the new variable with the old one, and that's your answer. So let us increase the level of difficulty, step by step. So, for example, let me ask you to calculate the integral of the square root of 5x plus 1 dx. So it means that I am looking for a primitive function for a square root of 5x plus 1. This is something that you couldn't do so far. Of course, if I ask you to do this one, it is easy, because I am asking you to find the primitive function for that, So this means that you immediately write it like this. But I want you to understand, in this case, even if you write it as 5x plus 1 to the power of 1/2, if I ask you what a primitive function of this is, you will not be able to answer immediately. So there are some cares that you have to pay attention a little bit about the details here. If you don't believe, you can use the same method exactly that we did for this one and get an answer here, and then differentiate it. You will see that you will not get that answer. For example, if you say a square root of x, if I ask you what is a primitive function for that, so you would say that, okay, I will change it to x to power 1/2. Then I know what to do with this one. It becomes x to the power of 1/2 plus 1 divided by 1/2 plus 1. If you calculate that, it becomes 3/2, so it becomes 2/3 x to the power of 3/2. This is your primitive function, yes? But if you want just to do the same thing here, so you will get what? If you want to do the same thing, exactly, copy and paste of this method there, at the end you will get 2/3 of 5x plus 1 to the power of 3/2. Agree? But now let us differentiate that, because if your claim is correct and this is a primitive function, it means that its derivative should be this function. But you see that there is a constant that it doesn't take care of that. If I ask you what is a primitive function for this, what is the derivative for this, you would say that I will write this. I bring 3/2 down. I will subtract 1 from the exponent, which becomes 1/2. But you don't stop there. You have to multiply by the derivative of the base, which is 5. But now let us see what happens. Yes, that's correct. These two are cancelled. That is also correct that this is 5x plus 1. But this is not correct. So you see, you get an extra factor of 5, which is missing. But of course, now you understand what the answer is. Because if the derivative of this one is this, if you divide the whole package by 5, you get the correct answer. Yes? But that's the point. You don't want to do it every time case by case to see if it works or not. So let us try to understand. First of all, I want you to understand that if you want to copy and paste the same method for square root of x exactly for this one, you will end up with a factor which is not correct. So this, what I have to do, I will do this. I will say that let this expression 5x to be u. Okay, so I will give this a name. Then after that, everything should be clear. What is the next thing that you do? You differentiate it with respect to u itself, so it becomes 1. You multiply it by u, du. And then you differentiate this, it becomes 5. And you multiply it by dx. Okay? And then the point is that to get rid of the old variable, the question mark becomes equal to integral. Instead of 5x plus 1, I can write u, so it becomes the square root of u. But be careful, this is just dx. You cannot write du there, because du is 5 times dx. So this motivates you to find dx. So what is dx? dx is 1/5 of du. And this 1/5 is exactly the one that will cancel that extra 5 at the end. Okay, so what you need to do instead of dx, you put 1/5 du. But of course, a multiplicative constant can be pulled out. You don't care, you just care about the function. This becomes integral of that. But then this is not a trouble. I want you to understand that's not a circular argument. I am taking the integral of this, but u is variable. Here it was different. I was calculating the integral of this, but x was variable. So what you see here is not what exactly appears here. But now they are exactly the same. So it means that I can use the formula. So the formula, exactly like u is x. So this becomes 1/5. Yes? But I have already done that, so let me just use that. I have already done that for the square root of x. I got this. Square root of u will be the same, but instead of x, I will have u. So this becomes 2/3. And then u to the power of 3/2 plus a constant c. But I can simplify this, it becomes 2 over 15, and u to the power of 3 over 2, instead of u, I write this expression. So it is 5x plus 1 to the power of 3 over 2 plus a constant c. And now you see that the correct answer is 2 over 15, but if you just did it like that, you got 2 over 3, which is wrong. Okay, so this is the correct answer. Okay, hopefully you understand the method, but of course it needs a lot of practice because some of them are not that easy to detect. So is that clear at least? The method is clear. Okay, so let us just try to give you more examples. For example, let me ask you this question. The integral of sine to the power of 5x multiplied by cosine x dx. So we want to calculate this. I am asking for finding a primitive function for this function. So it means that when I differentiate that function, it turns out to be sine x to the fifth multiplied by cosine. Okay, so this is not a standard problem so far because you didn't know how to do it. But now we want to learn how to do it using this method. The only thing is that I told you, you have to train your eyes so that you can catch the pattern. It's not that hard. You look for a function so that its derivative somehow appears in the expression itself as a multiplicative expression. Okay, so can you tell me what is that? It's very clear. What is the function whose derivative is also appearing there? Is it sine or cosine? Of course, you might say it is cosine, but the sine is correct because the derivative of sine is cosine. The derivative of cosine is negative sine. Negative sine is not a matter because negative sine is just minus 1. But the derivative of cosine becomes sine, not sine to the fifth. So you have to take this one. If you want to test, to do some trial and error, it would be worthy if you take this u one to be sine x. So you would write let this, and the rest of it is algorithmic. This is the hard part to guess what is a good choice for your new variable. But the rest of it is algorithmic. Okay, so it means that you take the derivative of this, which is 1, you multiply it by du. You take the derivative of this, which is cosine x, but you multiply it by dx. Everything now becomes very clear, yes? Because then the question mark is equal to the integral. Instead of this expression, I put u, so it becomes u to the 5. But instead of this whole package, I can write du. There is something that you need to know. When you do this, there shouldn't be any track of the old variable at all. So every variable that you see here is u, no track of x anymore. But can you calculate this integral? It's extremely simple, yes? You see, this integral is, the function is u5, but u is considered to be the variable. So then what is the answer? This is 1/6 of x to the, u to the power of 6. And then you add a constant again. Okay? But what is u? U was introduced by me to be sine x, so at the end I have to replace that. So it becomes 1/6 sine to the power of 6x plus c. That is your function. Let us test the idea. Let us see that if I have done it right. To test the idea, I have to take the derivative of this function and confirm that the derivative becomes exactly this combination that you see. But let us do it carefully. So this one, I want to take the derivative. 1/6 is a constant. I just pull it out and concentrate myself on taking the derivative of the function part. But hopefully you haven't forgotten differentiation. That is the chain rule. So you need to give the role of u to this in your head. it becomes u to power 6. So it becomes 1 over 6. 6u5, yes, 6u5, which is sine to the power of 5. But it is not finished. You have to multiply by the derivative of u, which is cosine. And then what happens, this is and this one are cancelled, you really get this function that you were looking for, yes? So this gives you the primitive function for that. Yes, is that clear? Yes or no? Are you confused? Okay. So let us now go to another one. So what about this one, do you think? Integral of ln of x over x dx. Okay, I want to wait a little bit for you to see that how you can solve this. It's extremely simple, but you need, I told you, you need to learn the trick. Okay, so what is a good choice for you?
ln of x.
Yes, it is extremely simple, isn't it? So if I take ln of x to be u, then I start writing du is equal. I have to differentiate this function. Hopefully you remember. It's 1 over x. And then you have to multiply by dx. Yes? If you want to, I just do it, but you really don't need to write it down. You can actually rearrange this a little bit so that it actually manifests that combination. So this becomes ln of x. Instead of this one, I can write this in my head. But then it's extremely simple because this combination has a name in u, which is du. And this is just simply u. So you see that the answer is integral of u du. So you see that this integral might look complicated in the first place, but it is not, because that is just u du. But this is what? Because the variable is also u. The answer to this is 1/2 u squared, and then you have a constant c. But then you don't forget, you have to replace u back, yes? So this means that this becomes ln of x to the power of 2 plus c. That is the function that I was looking for. Its derivative is that. Okay, let me write another one for you. Yes, this is good probably. So integral of 1 plus tan squared x divided by square root of tan x. And then you have dx. So don't worry about this integral sign and dx. This is just asking you, give me a function whose derivative is this combination, which apparently seems a little bit complicated, but we can do it now. This is, I told you, you need to train yourself. This is the most important trick in calculus integration. You need to think in this way. Is there any function whose derivative somehow appears in my function as well? Of course, up to a multiplicative constant. Multiplicative constant, it doesn't matter. Yes? Yeah. This is the guideline. If you think in that way, you will probably understand what to do. Okay, so let us finish these two, and then we stop the lesson. We continue the next part, the next session. Okay, so did you come up with an idea for what is a good choice here to be u? Of course, you need to know the formulas for derivatives very well, okay? If you have forgotten about them, there is no chance, because you have to think in this way. So, do you have any idea what to do? What is a good choice for that one? Yes?
Tan of x.
Tan of x, yes? Because if you remember, if I say u to be tan of x, then du is equal to, the derivative of tangent is one of the formulas that I told you to remember, is this combination, yes? The derivative of tangent, we studied in Math 4, it's 1 plus tan squared, and then you put dx there. And then everything becomes clear, because that combination in the numerator is just nothing except du. So the question mark becomes equal to integral I would write 1 over square root of u instead of tan of x. I just replaced u. But this combination multiplied by dx can be written as du. It's 1 over. Of course, sometimes you can also put du here. It doesn't matter. But this is a Mat 3C problem, yes? You want to find the primitive function for this combination. What you're supposed to do you remember? You need to write it as u to the power 1/2 and bring it up so it becomes u to the power of -1/2 du. But this is extremely simple, so what you do, you write u to the power of -1/2 plus 1 divided by -1/2 plus 1 and then plus a constant. That's it. Integration part is finished. Let us simplify this a little bit. -1/2 plus 1 is what? Is 1/2, but 1/2 is in the denominator, so it goes to the numerator and becomes 2, and then you have u to the power of 1/2 plus c. But u to the power of 1/2 has a better name, so I just call it square root of u plus c. But at the end, you have to replace u with what you have introduced for. This becomes 2 square root of tangent of x plus c. So it means what? It means that if you differentiate this function, which you should be able to do that immediately using the chain rule, you will get that combination that you see here. Yes. Okay, what about the other scenario? The other integral. So if you don't mind, I don't want to change. Let us just do this one. So what is a good choice here for u? Do you have any choice for u here as well? Again, this is a good choice for u. Why is that? Let us see. Because if I take u to be 3x squared minus 2x plus 1, du becomes the derivative of this, which is 6x minus 2, and then times dx. You might say that, okay, the derivative didn't appear there. Of course, it didn't appear exactly, but that is just 2 times that expression there. So it doesn't matter. So you see, you divide everything by 1/2. So it becomes 1/2 du. On the right-hand side, you get exactly the combination that you need, which is this combination. So then it means that this question mark is equal to integral. Instead of this combination, I can write 1/2 du. And instead of this combination, I can write the square root of u. But this 1 over 2 is just a multiplicative constant, so I bring it out. Then I will have the integral of this one. But if you don't mind, let us just copy and paste what I got there, because that is exactly that integral. Yes? And the answer was this one, so I just copy and paste that one. But there is only one difference, that there is a 1/2 here. So I would write it as 1/2. This integral is 2 square root of u, then plus a constant. So everything becomes a square root of u, but u is that guy. So this becomes 3x squared minus 2x plus 1. And then you have a plus c at the end, yes? So this is the function whose derivative is. So I will bring you more harder examples next time, because I think it is good that we practice this very well and then we move to the next part of this lesson. Okay? Any questions? Okay, thank you. You can practice on your own after that, and the lesson is free. Thanks.